Tonight, man stands on the threshold of outer space. Now, since the Russian satellite was launched a week ago, it's covered some 3 million miles. Well, does this now mean that space travel is a practical possibility? Can man build a vehicle that will take him not only to the moon, but to the planets as well? And having built one, can he equip himself to survive in the emptiness of space? And in any case, what practical benefits can we expect from man's first big step away from the Earth? This is what Frontiers of Science looks into tonight. And in the course of this program, you will see the forerunner of a spacesuit developed for the RAF, and this will be the first time it's ever been shown publicly. But first of all, let's hear from Sir Harold Spencer-Jones, the Astronomer Royal.
Well, let's look briefly at what has gone before the launching of the Russian satellite. I have here a globe 6 foot diameter representing our Earth, on which, however, the mountains are shown in a very much exaggerated scale. Now, on the scale of the size of the Earth, I have here 5 little pins. The smallest of them, about a 20th of an inch long, represents Mount Everest, 5.5 miles high, the highest point on the Earth, which man succeeded in climbing after many failures. Here we have a longer pin representing the greatest height which man has so far reached above the surface of the Earth. Dr. Simons went up in a balloon not so very long ago to a height of nearly 20 miles. But small animals, mice and monkeys, have been sent in rockets to a still greater height, 37 miles, represented by this pin. During the war, the Germans launched the V-2 rocket. Many of you no doubt have very unpleasant memories of that, which reached a height of about 125 miles. And this largest pin represents approximately the height at which the artificial satellite is traveling. Now, just let's look for a moment at what is involved in launching an artificial satellite. It's projected by means of a 3-stage rocket, which is fired vertically and turned over, and when moving in a horizontal direction, the satellite is projected. Now, if the speed of projection is not sufficient, the rocket will travel a certain distance over the surface of the Earth and fall down to the Earth. With a higher speed, it will reach a greater distance, but if we get to a speed of 18,000 miles an hour, or 5 miles a second, it will not fall down on the Earth. It will be continually falling, but it will completely circle the Earth, its centrifugal force just balancing the force of gravity. Of course, one likes to have a margin for error, and so it's projected with slightly higher speed, and in that case its distance, the point opposite its projection, is somewhat greater than the point from which it's projected. Now let's think of going beyond that and increasing the speed still further. In that case, the orbit becomes more and more elliptical. At the point opposite the point of projection, it's further and further away from the Earth, until when one reaches a speed of 25,000 miles an hour, about 7 miles a second, the orbit opens up, it doesn't close, and the vehicle will go off into interplanetary space. I have here, just to give you some idea of what these little bodies are like, an actual scale model of the American satellite showing the instrumentation, very complex instrumentation. Here are the aerials for transmitting signals to the Earth. The Russian satellite is not instrumented like this. It merely has batteries and radio transmitters for sending signals. Now, in going out into interplanetary space, of course our first target would be the Moon, because that is our nearest neighbor in space. And here is a model of the Moon on the same scale as the Earth, about half the diameter, about 1/64th of the volume. I can't in the studio show the Earth and the Moon correct to size and to distance, so we had these models taken out into a field and photographed, and there you see them in their correct relative distances, 180 yards apart. Here I have 2 small models representing the Earth and the Moon, correct to scale with their distance apart. Now, if we shot a body straight off from the Earth to the Moon with a speed of 25,000 miles a second. It would take roughly 10 hours to reach the Moon, because the distance of the Moon is about 250,000 miles. Actually, of course, one would send it off in a curved path, starting in a direction parallel to the Earth. And I think the first thing that should be attempted is to send a small unmanned satellite around the Moon, the back of the Moon, to take photographs of the back of the Moon which man has never seen. To send manned satellites, of course, is a very much bigger problem, because you have to have larger satellites and heavier and so on.
Well, thank you very much indeed, Sir Harold. I introduced you as the Astronomer Royal. Of course, you are the former Astronomer Royal. Well, you seem remarkably confident about our ability to get to the Moon. But meteorites, don't they present really serious hazard?
Well, they do present a hazard. Here is a meteorite. This is one of a number of chunks of matter which are wandering about through space. Most of them are very much smaller than this, many in fact smaller than the pea, but there are thousands of millions of them which come into our atmosphere every day. They do certainly present a hazard. It's difficult to estimate how serious, but the chance of being hit by anything as large as this is certainly extremely small.
Well, one wouldn't like to be hit by one, but Sir Harold, the last week you wrote in a magazine that you thought travel to Mars and Venus would be quite out of the question. Now, on what grounds did you say that?
Well, I still think that, because, as I say, to get from the Earth to the Moon is a comparatively short journey, something over 10 hours. But to get to either Mars or Venus means a journey of many months, possibly a year or longer. And that means a very large vehicle to carry the men, together with their food and drink and supplies of oxygen and so on. And it does increase to such an enormous extent the complexity of the problem that I can't see it being done for centuries.
Yes, but I say, apart from time and carrying food, surely there must be greater problems than that, aren't there?
The problems of
actually travelling to Mars.
Well, there are problems of navigation. Navigation in space of 3 dimensions involves quite a number of problems. They're rather technical. It would be necessary to carry an electronic computer, I think.
Mm-hmm. Well, Sir Harold, as an astronomer, what practical benefits do you think will come out of all this?
Well, of course, many people look forward to building a station out in space, a space station, and to setting up telescopes and other instruments on it. And if that was achieved, it would undoubtedly have very great scientific value, because we could get all sorts of observations, astronomical and others, where we are not hampered by the dense atmosphere through which we have to view things from the Earth.
Well, thank you very much indeed, Sir Harold. Well, sir, it seems that the astronomers are pretty confident about our ability to be able to travel into outer space and certainly to the Moon. But the engineers, are they so confident? Just how big are their problems?
10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
Now, this is the British Skylark rocket, which you just saw being launched at the Woomera rocket range in Australia. But this little piece of hardware only travels up into the sky a mere 100 miles or so. So obviously there are great technical engineering feats that are faced or have to be faced by engineers like Dr. Alex Baxter, who was formerly a professor of propulsion at the College of Aeronautics, Cranfield, and is now chief executive of nuclear engineering and rockets at de Havilland. Now, we always seem to assume that to get into outer space, we've got to use rockets, Dr. Baxter. Now, why exactly have we got to use a rocket?
Well, the answer is quite simply that the rocket engine is not only the most powerful type we know, but it's the only one that will work outside the Earth's atmosphere. And the reason for that is that it carries its own oxygen with it to burn with the fuel, instead of trying to use the oxygen in the air as other types do. Now, in this Skylark, for example, the oxygen is combined with the fuel in a solid propellant type, rather like a firework. But in some of the larger rockets, it's much better to use a liquid type. And here, for example, we have a simple experiment that demonstrates how the oxygen may be in one tank as a liquid and the fuel in another tank as a liquid, forced out into jets and then squirted out into the rocket, forming a gas which is forced out of the chamber and gives the urge which is necessary to push the rocket forward. Now you will see the jet, and there is the flame operating, and that is of course quite a small jet compared with the rocket's requirements, such as the Russian satellite. There we might have used something like 100 gallons a second. Well now then, to put that into a rocket means very large tanks. So perhaps we ought to have a look at a rocket, see how the tanks fit into the thing. Here you see the oxidizer tank and the fuel tank, and they are pushed out by pumps or by pressure into the combustion chamber and ignited, and then the gases come out through the exhaust at the back, and at very high velocities the reaction pushes the rocket forward. Now the speed at which that gas comes out is very high, it's very high temperature, and you can see a film of this occurring, a jet coming out, which is shows the high speed and high energy that is available, and you may be able to see the shock pattern, the diamond formation, which is characteristic of all rockets. Now if this is all successful, then we have got a problem to consider with regard to the weight of the rocket. Now we want to get as much propellant into the rocket as possible and yet make it as light as possible. And you will see a diagram which shows the V2. If we make the structure of that one unit, the V2 carried something like 3 units of fuel, and that gave it a speed of about 1 mile a second. Now we can improve on that nowadays, and 1 unit of structure will give us perhaps 7 units of fuel, and that would give us something like 2 miles a second. But that's a long way still from the 5 miles a second that Sir Harold Spencer-Jones mentioned for an orbital rocket. And to do that, we'd need 49 units of fuel to 1 unit of structure. And to escape to the moon, we'd need something like 99 units of fuel and 7 miles a second.
Well, that looks certainly a very much bigger rocket than the others. Just how big would it have to be?
Well, I think perhaps we might compare it with I think before we compare it with that, we should consider a way of escaping from the Earth with a 3 multi-stage rocket, because that would be a very heavy rocket. Perhaps that one would weigh something like 1 ton of takeoff weight for a pound, 2 pounds of payload. But we can overcome that structural problem by using a rocket which carries another rocket at 2 miles a second, drops away, and the second rocket will then go forward at another 2 miles a second, giving you a total of 4 miles a second, and a third stage would accelerate to perhaps 6 miles a second. So in that way we could get to velocities which would give us space conditions. Now from there we can consider the size of such a rocket, and I think that if we considered it in relation to Trafalgar Square, you would find that we had something which would hide Nelson's column.
Well, now, it seems to me, Professor Baxter, from what you just said, that the greatest problem facing you as an engineer is to find a powerful enough and light enough fuel which won't take too much space off in a rocket. Does this mean you've got to wait for nuclear engineering to power one? Nuclear power?
No, I think there are better fuels perhaps just round the corner, but we couldn't yet use nuclear power, because after all nuclear power plants are a very heavy thing, and we've been emphasizing how light this must be. So I think in the future we may get that, but it's rather a long way off.
Now, just how soon do you think we'll be able to get?